Ionization of molecular compounds. So a molecular compound, which as a reminder, that means not ionic. So that means not a metal and a non-metal. Molecular is non-metal, non-metal. Some of them can dissolve in water if they are polar. Remember, we have levels of covalency. We have like polar covalent and non-polar covalent for our molecular compounds. So we do have like extremely polar molecular compounds. An example of that would be like hydrochloric acid. That's a hydrogen and a chlorine, so two nonmetals. So we do consider it like highly polar covalent. And in water, it will dissociate and form ions. During that process, during the dissolution process, there's small amounts of heat that are released, which aid in breaking those covalent bonds. Polar molecules will dissolve in polar substances. So water is polar. So anything that is polar or ionic will dissolve in water. And then anything that is non-polar covalent will dissolve in non-polar solvents. The one that we typically will reference is either like hexane or benzene or toluene. Those are the three that you guys you'll see those terms. Hydronium ions, that is this H3O plus here. That is what will make something acidic. So when we have something like HCl, and we know that it is an acid, that means in solution, it's going to create that H positive. Well, in reality, it's actually creating H3O positive. The water is taking the hydrogen from that chlorine, producing the chlorine plus the hydronium ion. The hydronium ion, again, is what's responsible for making things acidic. When we shorthand it, you guys will see it as like H plus sometimes. So for when hydrochloric acid dissociates, you get H plus and Cl minus. Sometimes we write that water symbol over the arrow, and then sometimes we write it here. There should be a plus sign here. Sorry for that typo, guys. But the water plus the hydrochloric acid will create H3O plus and Cl minus. So this is in reality what's happening. When we do dissociation, we tend to write the water over the arrow and just have the H plus and the Cl minus, sort of like as a shorthand. But technically, in reality, this is more correct. A strong electrolyte. Polar molecules tend to make strong electrolytes. That means that they can conduct electricity. So acids, which is what you saw before, and here it is again with the plus. Acids make strong electrolytes because they create ions. Ionic compounds also make strong electrolytes because they make make ions when they dissociate. So anything that can dissolve, anything that's like polar and can dissolve in water will make a pretty strong electrolyte. Now, the less polar you are, the closer you get to nonpolar, the weaker and weaker the electrolyte becomes. And eventually you would get to like a nonpolar molecule, which wouldn't dissociate. It wouldn't create the positive negative charge. Therefore, it can't conduct electricity. And that would be a non-electrolyte, or a non-electrolytic solution. So weak electrolytes, again, the closer you get to nonpolar, the less ions are created, giving you a weaker flow of electrons. In order for electricity and an electrical current to run through, you need electrons to be able to flow, which means you need those charges present, passing those electrons on. A small amount of dissolved solution exists as ions. So again, that means we got closer to nonpolar, right? We had a weak electrolyte, therefore we have a weak electrolytic solution. An example of that is when we talk about acids. We have strong acids that will dissociate completely, and we have weak acids that won't dissociate completely, and we use this double arrow in the middle to denote that. So anytime you have a weak acid, you're going to have this double arrow. That means that this acetic acid and the water in their liquid forms are present. Also present is the two ions in their aqueous forms. Remember, aqueous means dissolved. So the acid will dissolve, but the reaction goes the other way too. So it might give up that hydrogen, but it's also going to take it back. The reactant side of this equation is the part that will not conduct electricity. There's no charges. The product side will conduct electricity because of those charges. So because both of those are present in the solution, that's why we get the weak electrolyte. Whoops. Sorry, I went the wrong direction. I wanted to go back here real quick. Here, hydrochloric acid is a strong acid. So we see the arrow going one direction. Again, it's a strong electrolyte, which means once I mix these two, the only things present in the solution are these ions. So a lot of ions is a strong electrolyte. Here, because they're both present, we have things that aren't ions present. That makes it a weak electrolyte. We will test electrical conductivity, whether in class or virtually, depending on which kind of student you are. We will practice conducting electricity. When a light bulb doesn't light up, that means that there's no electrical conductivity. That means that there's no ions in there. So the example here says ethanol. Pure water would do this too. Not tap water. Tap water does have like stuff in it, but DI water, distilled water, would also do this too. There's no transfer of electrons. There's no ions in there. High electrical conductivity would give you a bright light. That means plenty of ions there to connect those two plates. And then a weak electrolyte, again, that would be something like acetic acid that we just saw on the last slide, would be a weak acid, which there's the molecules that are present, but then there's also the ions that are present. So weakly conducting electricity. I like to include colligative properties here because we're talking about dissolving, like the dissolving process. And that's what a colligative property is. I mean, it's the number of solute particles dissolving in a given amount of solvent particles. So it's still that dilution process. We can like use the properties of the solute. We can use that to adjust physical properties. So I mean, I'm the example I'm trying to get to is like if you live in a state that has a lot of snow, and you drive a car. Well, we know when water freezes, it expands. We know water freezes at 0 degrees Celsius. If you live in a state where it snows a lot in your car or even in your home, really, if it gets below 0, which it does frequently for a lot of homes, for a lot of states, it does get below 0. And when that happens, in Fahrenheit terms, right, that's below 32 degrees Celsius. It definitely gets below that. So, water would freeze. So we use things like antifreeze to make sure that doesn't happen. What we're doing is lowering the freezing point of water. We call that freezing point depression. So we can do that using colligative properties. We can take whatever the solute is and add it to our solvent, dissolve, and that will then lower the amount of energy required or the amount of energy released in order to reach a freezing point or a boiling point. We can also do that with pressure. We talked about that in the last chapter, how if you take water to a low pressure zone, you can boil it at a much lower temperature. We can also do that with like adding things to it. We can boil it at a higher temperature or a lower temperature, which again is that dissolution process. We aren't going to calculate colligative properties this year, but we might. I'll get back to you on that. If you have any questions in general about this, please let me know. Thanks.